Hello everyone, welcome to Stochastic Calculus for Finance 1. This is section 4.4 where we start talking about general American derivatives. And the goal in this section is really to talk about American derivative securities whose payoff can be really path dependent. Then we define the price process for this type of securities. Then study the process, the property for such processes, right? And then we talk about how to really hedge path-dependent American derivatives. Then from here, we'll go and study the optimal exercise time. Like for these American derivatives that are path-dependent and that can be exercised at any time, how can we really find the optimal time to exercise this type of derivatives? So that's what we will cover in this section. All right. So first, I will give like a general definition of these path-dependent American derivatives, and with this like very general definition, we'll have a better tool to really understand these type of securities. So first, we're still in the end period binomial model that we have seen before, and then here we define this variable, this value. All right, I will call it Sn, but this is not really S. This is like just. And this is just like a set of all stopping time tau that take value in the set from small n, which is like the time we're looking at today, to the end of the time period when the option is expiring, or plus infinity. And I will give more color as to what this thing really means. And we can call Gn a random variable that depends on the first n coin tosses, right? And this Gn basically can be path dependent because it depends on the first n coin tosses. So how you get at period n can matter. So we say like an American derivative security with intrinsic value process Gn is a contract that can be exercised at any time, at any point in time, n less than the greater than capital N when the option is expiring. That payoff like this value Gn when it's exercised at time n. And now, if we're trying to understand the value process of the price process of this contract, then we can use basically this relation here using the risk neutral pricing for American derivatives that are path dependent. So there's like this relation here that may look quite complicated, but we can go through it very quickly and try to see if we can understand it. So that means here the value of the derivative security, basically we have a stopping time, right? And the stopping time is going to tell us basically how do you want to exercise, like when do you want to exercise, what is our exercise strategy, right? So we can have many exercise strategies. So we would want to find like the exercise strategy that will maximize basically the value of our option, right? Because we're here in the market to make money, so we want to be able to maximize the value of our option. So we want to find the optimal strategy to see how we can really exercise this option. And this stopping time or this exercise rule, like strategy that we can say, need to be inside delta Sn. And remember what is delta Sn is. It means like basically you can take value only from n to small n to like the end of the period, or plus infinity, meaning it will never be exercised. And that makes sense because if you're trying to value the option at time n, then definitely like we can the only point in time where we can exercise is today, time n, or we can exercise the option sometime in the future, or we can just never exercise the option, right? It doesn't make sense to have to consider tau, for can be like basically n minus 1. I mean, if the option was exercised yesterday, then why are we trying to price it today at time n, right? So that's why basically where this part is coming from. It's telling you like the exercise can happen only either today, you can exercise today, or sometimes in the future. And this max means we want to find a strategy that will maximize the value of our option. So great. And then we can move now inside this expectation here. So this is basically an indicator function. So we're saying like basically if this random variable tau is If we want to exercise it sometimes between today and the end of our period when the option is expiring, if we really want to exercise sometimes there, then this indicator function will be 1, right? However, if tau is not less than or equal to n, that means greater than equal to n, that means like tau has to be plus infinity, right? That means like we're never exercising it. So if this relationship here is not true, then this indicator function is 0, so that we can multiply 0 by whatever is over here, so that we get 0. And that means like basically never exercise the option. And if you don't decide to never exercise the option, then the value when you don't exercise the option, you just get $0, right? So that's basically what this part is telling you. So if you're not exercising the option, this thing is 0, which means like the whole stuff will be 0, and which makes sense. Like we're not exercising the option, we're not losing money out of it. And here, okay, so let's look at here. So tau minus n. So let's say like basically this is the time period, and this is n today, and we decide to exercise at some point in time tau here, right? So that means like we just need to figure out the payoff at this point, and we need to discount it today. So we're going to discount it, and the time period we're going to discount it by is going to be by tau minus n. I think that makes sense. And g tau. So depending on where we're exercising it, we're going to have basically a payoff, right? A certain amount of money we're receiving by exercising the option. At some point in the future, we just find that payoff and we discount it to the present. And that's all that's what all like this complicated looking formula means. It can be very simple to understand when you have an idea about what this formula mean. Okay, so let's use this basically to show that basically that if expiration occurs, if exercise of the option occurs only at time n, right? For example, then basically the payoff would be given by this function, right? How much do I get if I exercise the option at maturity, and and the minimum that can be is 0, meaning we just don't exercise it. So let's try to see how we can use this. So if you say V capital N, so that just means like we want to maximize given like an exercise option tau, which is delta S capital N, expected value as written at time n in the real natural world of I tau less than equal to n, and then we discount R. So tau minus n j tau. Okay, so how can we go from this to show that this is actually nothing but this? Okay, so the tau needs to be inside this set, right? So that means like our exercise rules, tau can either be basically n, right, or tau can be plus infinity, meaning that at time n we either decide to exercise the option, or right, and that tau will be n, or we decide to not exercise the option, meaning tau will be plus infinity. So we have only two cases, right? So if tau is equal to n, like we decided to exercise the option, so that means like Vn will just be basically E tilde n, and this guy here would be 1, right? This thing would be 1 because tau would be less than or equal to n, right? So 1 time okay, so tau here will n is capital N here, right? Because that's the time we're talking about expiration, and then this tau here is basically n as well that we said, right? Because we're assuming that it's exercised at time n. So all this would basically be 1. So this will be 1 time j tau is n, so j of 1, right? So this is one case of what can happen. Or we say we never exercise the option. So that means Vn can also be Vn, and then the indicator function here, since it's plus infinity, so this is 0. So this is basically 0, right? So this is like the two value that n that Vn can take, and we want to take the maximum out of those two. So that's the same thing as saying we want to take the maximum of and not here, like expected value at time n of Jn is nothing but, we can take out what is known. This is nothing but Jn, right? The payoff. So maximize the 0. So that's basically where this thing is coming from. If, for example, we have a European option, then we know that basically for European option, like this exercise rule can only be at time n, right? And then, for example, if it was a call option, we'll just get max of basically the payoff function and 0, right? And that's what we're basically showing here. If we're at time n, then this is the expiration rule, and we can derive that exactly from this formula. And so that kind of shows, maybe give us confidence that this crazy looking relation actually works. It's very general. Okay, so let's use this and try to see how can we price the American put option that we have shown before, right? And if you remember well, in the previous video, we had like this tree for the stock price, right? The stock price starts from 0 and can take this different value over time. And we had like a put option, American put, with strike of 5, and we have seen this this security in the previous video, and so we're going to try to price this security using the formula that we've just found out now. And when we did that back in the days, in the previous videos, we found like basically using the tree that this would be a different value of this American put at different nodes on the tree, as we have seen before. So for example, the value of the put at time when we get to ahead was 0, because the payoff there would be 5 minus 16, which is obviously negative. So because it's negative, you're not going to exercise the option. You're just going to let it expire and you get $0. So and again, this is exactly what we have seen in the previous video. So now we want to be able to price this option using like basically these general rules that we just derived for American derivative securities. And this could account both for path dependent derivatives or non-path dependent derivative securities. Okay, so to do this, we basically need to find first like these J's, right? The intrinsic value at each point on the node. And that's what I have provided here. So here basically it's minus 11. So if you exercise at this time when the stock price is 16, so 5 minus 16 is equal to minus 11, right? And that's where basically this minus 11 here is coming from. And we do that for each node on the tree to really find what is the intrinsic value. And that's because we need these J's. So once that's done, we have also shown that basically at the node at the end of the tree here, right, using this formula, using this relationship that we have, really like the formula can simplify to just this, and I've just shown that. Great. So okay, so using basically this rule, we can find basically if we get 2 heads, then it's 0. For these 2 guys, it will just be 1, and here minus 4, right? And that's what we're seeing exactly here. It's just basically the maximum of Gn 0. Where the Gn would be negative, we get 0. Where the Gn is positive, is greater than 0, we just get the intrinsic value, which makes sense. Now, consider the case where like the first coin toss was basically a tail, right? So if the first coin toss was the first coin toss is a head. If the first coin toss is a head, that means we're like at this tree, at this node here. Okay. So to find basically the value at time 1, we need to use this relationship here. So we just replace like this n here by 1, right? So tau needs to be now into this S1, and we take the expectation as return of time 1, and we want to find the optimal strategy really to maximize the amount of money we're making in this when we're standing at this node, the maximum amount of the value of our American derivative. And this is just the formula we have seen before. Now, okay, so again, as a reminder, like this, what this means is that the stopping time, the strategy can take value only in this set. So that means we can either exercise at time 1 or exercise at time 2 or not exercise at all, the option. And we find like basically the value to maximize this option, then we have to calculate it this way, which is just basically 0.4. And let me come show you very quickly what that means. So if I'm at this node, right, so clearly I don't want to exercise at time when I'm sending, with the first coin toss is ahead and I'm standing here, I clearly don't want to exercise at time 1, right? So that means basically this tau h THT cannot be 1, right? We cannot decide, we cannot say that we want to exercise at time 1 because it's negative. So actually the best strategy that we can do is, if we're standing here and the next coin toss is ahead, -11, don't exercise, right? So that means tau THH, we want this to be plus infinity. We don't want to exercise and lose $11 if we get another head. However, if we get like a head and then a tail, we come down to this node, we might want to exercise, right? So tau HT, we might want to exercise, and that will be exercising at time 2, right? So this is actually the best strategy that we can use. And doing that, basically, if you get like basically head, that means like tau is plus infinity. So in that case, this thing will be 0, right? The indicator function will be 0. So that's where like this 0 is coming from. And we're taking the expectation. We know like the probability of going up, there's no probability of going down. So and those are equal to 1.5. So that's where this is coming from. And if we in the other scenario, when we stand here, there's 50% chance that we come to this node, right? Where G1, where tau will be basically equal to 2, right? So J tau is equal in this case of H is just equal to J H and then tail, right? When we move on this to this node, right? So that's where, so that means like this guy would just be 1, right? And that's why basically there's a 1 here, which is coming from this side being equal to just 1, and 1 minus 1 is 0, right? So this whole thing would be 1, right? So you get a 1/2 at the point here, and then we just discount it. Yeah, and then we just take it and discount it. So tau will be equal to 2. Yeah, tau TH is actually 2, right? So this will be basically 2 minus 1, which is 1. So that's why we basically have to, this discount factor is coming from. Okay. And then when you do the math, you find the 0.4 for this node, which is basically the 0.4 at this node, which is good. Makes sense. Okay. Okay, so now consider the case where the first coin toss now is a tail. Okay, so if the first coin toss is a tail, that means like now we're standing at this node. Oops, let me go back. So if the first coin toss is a tail, now we are like standing at this node. And if we try to find the value at this node, then it's just going to be basically this guy here. Now here we have many different strategies. If I stand here, what are the different strategies that I can use as stopping time that can help me maximize the value of my option? So if I stand here, I can either exercise the option right now, and then I will get basically $3, right? Because that's the intrinsic value. So what exercise stopping time rule that we can use is basically TTH is equal to 1, right? And tau tt is equal to 1. So this means like we exercise today. Whenever we get to see the first coin toss is a tail, just exercise. So that's one possibility. Something else that we can do is just wait next period, right? So that when you get, so that means like if toe th is equal to 2, wait until next period to exercise, or toe tt is equal to 2 as well, right? So just wait, don't exercise now, just wait and then exercise. So we need to find, so I think these are like the more realistic role. But remember, actually you can see there's like another strategy you can think of. Like if I'm standing at this node, right, and I know that next time I will get a th, then just exercise now, right? So that would be basically a role exercise route that would be like toe th is equal to 1. If I know that I'm going to be at this node and just get this $1, then I just need to exercise. And then if I know I'm going to get to this node, to tt, then exercise actually at time 2, right? Because I get $4 instead of the $3 here. But this thing, but this case here is actually not a valid case. This isn't like a valid stopping time, because it's like we using a perfect crystal ball. And if you can remember the definition of a stopping time, right? So if we have like basically tau from 1 to n, right, and we say that that's equal to a number, then whatever happened after that, it should always be equal to that number. But you can see here we kind of violating that, right? Because this thing here in this first case we're saying is 1, and then but in the second case, when like just like the stuff after like the first coin toss is changing, we change the number. We cannot do that. We're violating the rule, right? So you can see here basically we're respecting the rule. The first one is tt, and we say okay, they're consistent. So the information, our decision to exercise is based only on the first coin toss, right? If you exercise at time t, then whatever happened after that, right, should not impact the value of our exercise time, because it has always been exercised. And this one also, we kind of like respecting that rule. So these two, you can see basically we say like in this case the value will be 2, and so this case also the value still need to be 2. This is the only case where we like violating this. It's like we have a perfect crystal ball to forecast the market. So this one we should not even consider this case. So the only two cases we have is either exercise today or exercise tomorrow, and we need to find between those two cases which one is going to maximize basically the value of our option. And it's fairly simple to see that if basically we exercise today, then we just get $3, right? So the first case, we can have basically the value of our option is just $3, right? Because if we exercise at time 1, this is 1 minus 1, and so this whole thing goes to 0, right? So notice discount, and we decide to exercise at time 1. G1T is 3, so that's all we get. And so the other case is we decide to exercise at time 2. So if we decide to exercise at time 2, then okay, so this guy here will be 1. We'll have to discount by 1 divided by 1 plus R, and J. Okay, so if you move at time 2, so J2, so that will be like, we can have a case where we have T, and then we multiply by 1 over 2, plus the other case, we discount by 1 plus R, we multiply by the probability 1 over 2, and J TH. So in this case JTT, that's like basically 4, this is 1. I'm just taking these values from here, and when you do all the math, you'll find that basically in this, if we go here in the future and try to discount in the present, then we find that basically the value will be based 2, and between 2 and 3 it makes sense then to exercise first at time 3, at time 1, where we get like the value of 3, which is higher. and and we've seen that that will match the value of the option at this point. Okay, so I think that's all I want to talk about in this one.